Hello everyone, let's pick up in the 1.5 notes where we left off. In addition to finding asymptotes, we can kind of describe the behavior at asymptotes, and we don't necessarily need a graph to do it. You can either plug in really close x values, or what I like to do is kind of make a sign chart after factoring. So let's take the limit as x approaches 1 from the right of x squared minus 3x over x minus 1. What I will do is factor this and then kind of reason my way through what's going on. If I'm approaching 1 from the right, I'm taking numbers very, very small, or very, very close to 1, that are somewhat small in terms of the denominator, but I really am just checking if this is positive or negative, because I know if 1 is an asymptote, which means if it doesn't cancel out, it will have an asymptote, and my behavior should either be approaching positive infinity or negative infinity. It would stand to reason we can just look through what the sign of each thing would be if I'm plugging in 1. So if I'm plugging in something slightly bigger than 1, say, like 1.1, 1.01, if I'm looking at this, x will be positive regardless of what happens. However, if I take a number close to 1 and I subtract 3, that's going to produce a negative. And if I take a number slightly bigger than 1 and subtract 1, it will still be positive. A positive times a negative is negative. Negative divided by positive is still negative, so it would be reasonable for us to conclude that the limit as x approaches 1 from the right is going to be negative. So if I'm choosing between positive infinity and negative infinity, it would be that we should be approaching, in this case, because it's negative infinity. Now, let's try doing the same thing from the left. The limit as x approaches 1 from the left of x squared minus 3x over x minus 1, same concept, but this time instead, I'm really approaching from a number slightly less than 1. Even though it's a number slightly less than 1, it'll still be a positive number, which means x will be a positive, x minus 3 will still be negative, but this time, if I take a number slightly less than 1 and subtract 1, I will get a negative in the denominator, so we know that positive times negative is negative, divided by negative will actually be a positive, so it would be reasonable to assume that the limit as x approaches 1 from the right of this function, x squared minus 3x over x minus 1, will actually be positive infinity. Now, reasonably speaking, even though the one-sided limits exist, generally speaking, we know that if the limits on either side don't match up, the overall limit doesn't exist. So we could reasonably say that the general limit for this function doesn't exist because these two don't match on part C. Now, the problem here is that you may have a lot of things going on in a function, and you need to know how to deal with infinities. And so when you're dealing with a composition of multiple types of functions, some of them may be infinite and some of them aren't, we need to have some properties of our number system to use to help us figure out what the limits are going to be. So the properties of infinite limits, it's not totally unlike how transformations affect your domain in some functions. When you think about the function f of x equals x squared, it's defined from negative infinity to infinity, and if you multiplied that function by a number, you would have to multiply the domain by a number, but 2 times infinity, since infinity is just a concept, it's still just infinity. Similarly, when you take infinity and you add or subtract a number to it, which would be like a vertical or potential horizontal shifts, it's still infinity or negative infinity, so it produces these rules. Let C and L be real numbers and let f and g be functions. They're saying we have 2 functions. One of them's limit as you approach C is a number. The other one's is infinity. That means if you add the 2 functions together, you would be adding the limits together, but infinity plus a number is still infinity. When you're multiplying, infinity times a number that's not 0, or that's at least positive, will still be infinity. But if you take infinity times a number that's negative, instead you will be at negative infinity. And if you divide, A number divided by infinity is still 0. Similarly, infinity divided by a number that's positive would be still infinity. Infinity divided by a number that's negative will be negative infinity. So similar properties hold for one-sided limits and for functions whose limit approaches negative infinity. So this is using positive infinity, but the rules still hold for negative infinity. So let's take a few limits that have multiple portions, and then we will be done with this section. So the limit as x approaches 0 of 1 plus 1 over x squared. So what do we know about 1 plus 1 over x squared? The limit as x, this is the same as the limit as x approaches 0 of 1 plus the limit as x approaches 0 of 1 over x squared. Now we know for a constant, the limit is just 1. But what happens as x approaches 0 for 1 over x squared? From the right side, you have a positive number squared in the denominator that's very small. 1 divided by something very, very close to 0 is positive infinity. On the left side of 0, you would have a negative number squared, but a negative number squared is still positive, which means that it's still going to be approaching infinity. So this idea here that we kind of have, quote unquote, 1 plus infinity, but really infinity is a concept, so that means the limit of the whole thing is going to approach infinity of 1 plus 1 over x squared. That's kind of a shorthand notation. I should write that. Equals infinity. I just got a little ahead of myself. What about something like the limit as x approaches 1 from the left of x squared plus 1 over the cotangent of pi x? That means, again, I'm dividing. I can take the limit as x approaches 1 from the left of x squared plus 1 and divide it by the limit as x approaches 1 from the left of the cotangent of pi x. I can just plug in 1 in this case because it's defined at 1, which means this is 1 squared plus 1, which is 2. What about the cotangent of pi x when x is 1? That's the cotangent of pi, which is cosine over sine. It's undefined. If I'm approaching it from the left, that's like cotangent of pi. Pi is at between the second and third quadrants. It's like I'm approaching it from the second quadrant. And we know that cotangent in the second quadrant is negative. So this should be approaching something like a negative infinity. When you take 2 divided by a very, very, very large negative number, it's going to be that the whole thing should be going to 0. Because when you take a small number divided by a very big number, it doesn't matter if it's positive or negative, it will get very, very close to 0. C is kind of similar. We say limit as x approaches 0 from the right of 3 cotangent x. That's really just the limit as x approaches 0 from the right. 3 times the limit as x approaches 0 from the right of cotangent x. Remember, you can take constant multipliers out front. Now, we know that as cotangent approaches 0 from the right, that's approaching it from the first quadrant. So that will actually be going towards positive infinity. So this is 3 times the limit that's positive infinity. But 3 times infinity, again, it's a concept, so the whole thing is just infinity. And lastly, we can look at the limit as x approaches 0 from the left of x squared plus 1 over x. We can split it. As x approaches 0 from the left of x squared, this is just 0. As x approaches 0 from the left of 1 over x, we're going to take 1 divided by a very small negative, which should give us a negative infinity, because we're taking a positive divided by a small negative, and 0 plus negative infinity means the whole thing, x squared plus 1 over x, as x approaches 0 from the left, is essentially decreasing without bound, which is what this really represents. So every time we say that the limit is infinite, we're really saying it increases or decreases without bound as it gets close to that value. And this is all of 1.5 and all of chapter 1 now.